Hello and welcome to this first lecture. In this particular lecture, we're going to look at some preliminaries and some data types that we'll be using in this particular course. And these data types are quite useful even if you're doing something unrelated to things that we will discuss in this course. But just a first word of caution, this is not a course on explaining the different physical processes or the different mathematics behind the various phenomena that we're going to discuss. However, we're gonna try to keep it as self-contained as possible. We're gonna look at some background, some theory, and then we'll look at the particular code. But all said and done, it will give you the confidence to tackle various problems on your own. And that is what. So first things first, you're gonna have to install GNU Octave. So just go to the website gnu.org/software/octave/index, and you're gonna end up on this page. You can simply Google GNU Octave. You can download this. Once you click on download, you get an option of what operating system you're working with: Linux, macOS, or Windows. In this particular case, I'm working on Windows, so you can go all the way to Windows and you can choose a 64-bit installer or 32 if you're using an older computer. And if you intend to use GNU Octave for handling very large matrices, you can install this particular package. But be careful, you need to have a sufficient amount of RAM in order for that particular version to work. The other thing that you can install, you can install Python 3, yes, that's fine, but you can also install Anaconda. You can install Anaconda and it will install everything in one go. So you go to, you Google Anaconda, anaconda.com, you go to products, individual edition, and then you do a download. It will install everything, just follow all the if you're using Windows, just download the 64-bit graphical installer and make sure you follow all the instructions. In particular, there's an instruction you have to deselect the addition of the path to the environment variable. So once you install this, you will have installed all the different packages that we're going to use in this particular course, and in particular, you will have a full access to all the libraries through a very easy installation framework. Lastly, you can install PETC. For that, you need to first have a working GCC compiler. GCC is a set of compilers released by the GNU group. So you go to installation. So once you download it, you can install it using /configure and then make all. Okay, it's not a very complicated installation, but yes, it does take a bit of time. And it's much easier to install on Linux than on Windows. But regardless, whatever we're going to study is independent of the platform. Whatever I'm going to show, Octave, Python, all that is available on all operating systems. Whatever you develop on Windows will run the same on Linux as well. So once you install Anaconda, once you launch Anaconda, you will be greeted by a screen which looks something like this. So you have CMD command prompt, JupyterLab, Jupyter Notebook, PowerShell, Qt, Spider. So Spider is something which is quite useful. So it's a IDE, meaning it's a integrated development environment in which you can write down scripts much in the way you would write down scripts in MATLAB. There are some other packages as well. Once you click on JupyterLab, it will pop up a window which would look something like this. So JupyterLab is an environment in which you make notebooks. So notebooks are file in which you can input text. So let me just click on this. So the beautiful thing about JupyterLab is that you can make Python programs as well as you can develop Octave programs. So basically it's a front end of these kinds of kernels. Okay, these things are called as kernels, and you can run whatever you want. So I have added into my JupyterLab these two kernels, Python 3 and Octave. By default, you will have Python 3 added, but if you want, you can add Octave as a kernel to this as well. Make sure you have installed Octave prior to installation of Anaconda. Let me click on this. So it will open a notebook style of file. So a notebook is something in which you input text, you input mathematical equations, you input scripts of code, you can embed figures. So it's a all-encompassing document which would contain all the things that one would need in order to encapsulate the entire idea. You don't need to write down documentation separately and the program separately and the figures separately. You can embed everything in one go. Once you're done, you can export the entire file as a PDF, as a Word file, as a LaTeX file, whatever. So these things are called as cells. Inside a cell, you can either encode a code or markdown. So markdown is a kind of markup language which is used to quickly write down text with headings, with equations, without really worrying about the formatting. In order to input markdown into this cell, I will select markdown. Let me put a title. So there's a very well-defined syntax for creating titles, for creating bullet points in markdown. So have a look at the markdown tutorial. I'm not going to discuss about that. And let's jump straight in into the programming part. So let me create the title of this file. So in order to execute a particular line, we would press Shift Enter. Upon pressing Shift Enter, you see that the title has been converted into a heading. Okay. So data types. So we've already covered the preliminaries of how to install these packages. Have a look at them. Take some time to read through the various installation procedures. It's very simple to do. Okay. Let's jump straight into it. The various data types. For the first and the most simplest data type will be that of a scalar. So in Python, we can define a scalar directly. Let us define a equal to 2. So let me change the kernel to Python. Okay. So a equal to 2, fine. Let me press enter and keep on inputting. So let me write b equal to -1, c equal to 4, and d equal to say 10. So now I've defined 4 variables, but I have not yet run the program. In order to run this particular cell, so things are encapsulated inside cells. Note that this particular cell by default, a new cell is created as a code. Whatever you write inside a cell will be interpreted as a code. If you want to interpret it differently, I can change it to markdown. So this will no longer be a code. This will be simply plain text. But I want it to be a code. So now I will press Shift Enter, and now it has loaded all the variables in memory. In order to check what variables we have, we can put this kind of a magic command. So Anaconda, JupyterLab, this kind of an environment has different kinds of magic commands. So this is one magic command. As we go in the course, we'll come across many other magic commands, and you can Google it and find out what are the different magic commands. So let me press Shift Enter. It will show me that I have 4 variables. The data type is integer and the data is this. In fact, let me make these as 10.0. Let me press Shift Enter to execute that cell once again. Now let me press. So automatically you will see that Python has declared d as a variable and its type is float, and the value it is storing is 10.2. And this is somewhat different from declarations in a much more imperative programming language like C, in which you have to declare a priori what the kind of variable will be. So in order to declare a as 2, you have to first write down int a and then later on you can say a equal to 2, or you can simply write int a equal to 2. So the same declaration in C would have been something like this. But this is not a course on C, and we'll continue on the style of Python. It's a very simple way of expressing your thoughts. So now let me just delete this variable block. So I can right click on this. I can say delete cells. Now let us perform some arithmetic. So I can press the escape key to focus on that cell, try it out. I can press enter to again come into that cell. So I lose focus by pressing escape. I gain focus by pressing enter. And the selected cell is shown by this blue border. Okay, so I press escape. I press M to convert the cell from code to markdown. Now I will write over here. So all you can do all of this with the help of all these the mouse things as well, but I prefer to do it with the help of keyboard shortcuts. So let me write down here some elementary arithmetic. Shift enter. So now that is interpreted as text. It is not a code, it is simply a text. Okay, so let me write down E is equal to A plus B, F is equal to A minus B, G equal to A times B times C, and D is equal to H is equal to A divided by D. I can execute this, there's no error. If there was an error, it would have come right below this particular cell. Now suppose I want to print out all the variables. Of course I can do whos again, and it will show me all the variables that we have. So E is equal to A plus B, 2 minus 1 is 1. F is A minus B, so 2 minus of minus 1 is 3. You can verify all these simple things. But another way of simply printing out a given variable is writing this print within double quotes. So we can write down the value of E is A plus B, okay, or E is, and we can write over here E, where A is equal to A and B is equal to B. Let me execute this. Upon execution, you will see that it has printed out this particular string, and wherever we have put down the variable, it will output the value of the particular variable. So for example, the value of E is, so this is printed verbatim. So this is printed verbatim, while this is the value of this particular variable. This particular thing is printed verbatim. Then we print the value of A, then this is verbatim, and then we print the value of B. So this is how you can put down meaningful print statements in order to make more sense of your code, and this is especially important when you are debugging certain codes. So debugging the old school style. Okay, so this is a very simple arithmetic operation on scalars, and we have also shown how we can print out the variables. Let us now move into how we can declare arrays. So there's a very special module in Python, it's called as NumPy. So we have to first import that particular module. So we will write import NumPy as NP. So the particular phrase as NP implies that NP is an alias for the packages inside the module NumPy. Python has a lot of modules, one of which is NumPy. There are several other modules called as SciPy or OpenCV. So OpenCV is a module for image processing. SciPy is a package for scientific computations. NumPy is a package for numerical methods and data structures. So there are various modules, but we will be primarily using NumPy and SciPy. So we import NumPy as NP. So let me press shift enter. Okay, so now we are in a position to declare arrays using NumPy. So NumPy arrays we can declare as a equal to np dot nd array, so n dimensional array, and then we have to give certain inputs to this particular function. So nd array is a function inside np. So in case you want to know the reference for NumPy, we can go to help, we can click on show contextual help, it will pop up this particular screen. We can double click on np and it will show the various functions that we have. So we have random, we have linalg, we have fft, we have polynomial. Okay, so we have a bunch of it will show a bunch of tools that exist. Okay, and of course NumPy has a very good documentation online, and you can always refer to the online documentation if ever in doubt. So ND-array is a particular function that exists inside the module NP. So when we double click on ND-array, we'll get the contextual help. So ND-array shape, the data type. Okay, this is what we need to give. So ND-array shape. So let us give. So let us make an array of size 5. So 5 d type equal to float. So let us print what a is. It's a random array. I mean, it's something which is 0 and it's of size 5. So 5 rows it has initialized. So this is essentially a way of initializing arrays. And data type float means whatever a will contain will be of type float. Okay, so in fact let me write down the let me show the variable space. So a is an nd array whose type is float 64, so it's 64 bit and it contains 5 elements. Now how can I access the different elements? Okay, so let me delete this cell. In order to delete the cell, we have to be out of focus from the cell and press D twice. It will delete the cell. Alternately, you can of course click on this particular cell. You can right click on it, you can delete cell. Okay, so we can declare various elements of a. So a0, let me write it as 5. a1 we can write it as 10. a2 we can write it as 11. a3 we can put it as -2, and a4 we can write as 6. So the indexing for an array starts from 0. And in case you have noticed this, whatever text I write after this hashtag is interpreted as a comment. So a comment is something which is not executed along with the code. Okay, so once I execute this, it would have assigned all the various indices of the array. So an array, so let me convert this cell into markdown. So an array is something like this: a0, a1, a2, a3, a4, a5. Okay, this is how that, sorry, I have to convert into markdown. Okay, so this is how that array looks. So now let us, since we have declared the different elements of that array, let us see how that array looks. So print a, oh, sorry, yeah. So now we have initialized the array over here. In this particular cell, we have declared the different elements of that array, and then we have printed out the elements of that array. Let me insert a cell above this. So the way to insert a cell is to press A. So let me convert this cell into markdown. So we can write initialize of an array with some user defined numbers. So this is how we declare an array. We can query the shape of the array. So suppose you are given an array, I can query. So np.shape of A. If I print this, it will show 5 comma nothing. So it's 5 rows, rather it contains 5 elements. So Python does not differentiate much if you're declaring an array between rows and columns. Okay, that is good. Now let us come to some different kinds of arrays. So we have initialized an array, but there are various kinds of initializations as well. So let us initialize B as np.zeros. Now suppose you want to know the function reference for zeros. So we just look. So zeros shape and data type. Okay, fine. So zeros. So let me define it as size 4, or let me make it 5, and d type equal to float. So now let us print B. It's all zeros. Let me define C as a linear space. So let me make this as a markdown. So a linear space is defined as an array which is having elements which are linearly spaced. So let us look at the syntax. So C is equal to np.linspace. So linspace has a it takes input A, B, and the number of points, where A is the first point. So let us say 1, B is the second point, and how many points you want between 1 and 2. So let me take 5 points. Let me print C. So C is an array which goes from 1 to 2. If you look at this over here, it goes from 1 all the way to 2, and 5 is the number of elements in C. So it has 1, 2, 3, 4, 5. So this is how we can declare a linspace. It's a very useful command. It will be extremely useful to define meshes, to define grids on which we will solve various kinds of equations. So this is extremely important. Another important function that is quite important, which is quite relevant for this computational course, is log space. So let us define D as np.logspace 1 to 4, and let me take 4 elements. Okay, so let us see what D is. So now log space, it defines a lean space going from 1 to 4, and it makes 4 steps. So 1, 2, 3, 4. These are the 4 elements that it will create. But now because it's a log space, it will make 10 to the power first element, 10 to the power second element, 10 to the power third element. So in the above expression, we basically have 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, because these exponents are what we have declared over here inside the function. So this is a very easy way of generating a geometric progression of values. Okay, it's essentially a way to generate geometric progressions. Linspace is a way of generating arithmetic progression, while log space is for geometric progression. Now let us add two arrays. Okay, so there's a very useful thing to do. So e equal to np.random dot normal 0, 1, 5 print e. So don't worry about what I have written. It's essentially I am using the NP module to use the random module to generate a normally distributed variable with average 0 and variance 1, and the number of elements is 5. So in case you are confused on the syntax, you can click on this and it shows. Okay, so location, scale and size. So we have generated E. So let me just quickly print out two things. But first let us save this file. I think it got saved. Yeah, it's saved over here. Let me rename this. So like 1. So let me print out some of the arrays that we can use to demonstrate. Okay, so we have these two arrays. The first array is A, the second array is E. So let us define B as A plus E, and let us print B as well. So we have added this. So it's an element wise addition. Okay, so this is an addition. So it takes each element of A and E, and so A0 is added with E0, A1 is added with E1, and so on, and it is assigned to elements of B. So this is a very simple way of doing element wise addition. Similarly, we can easily do element wise subtraction, element wise multiplication, but this is not recommended. It is not recommended to do element wise multiplication like this. It is better to do np dot multiply a comma e. So let us print out C, let us print out D as well. Okay, so this is how you obtain element wise subtraction. So you can easily verify using these arrays, and element wise multiplication as well. Similarly, we can do an element wise divide as well. So the beauty about using cells is you can modify it and rerun the cell. Whatever is there in the previously run cells, it stays, and that new cell that you're executing, all the variables inside that get updated. Okay. So yeah, so this is how you do element wise scalar operations. You can obviously add a single scalar to all this as well, and it's much easier. You can simply do, so let us make this simple scalar operations. So I can make C equal to 2 times A. Let me print out what C is. In fact, let me print out what A was as well for reference. So with the help of this, we have multiplied all the elements of A with the scalar 2. So scalar multiplication is quite straightforward. Just remember, when you're doing element wise operation between two arrays, in particularly multiplication and division, it is better to use np.multiply and np.divide. In fact, you can use np.subtract and np.add also, in order to avoid certain mishaps that can happen when you add elements. Okay, so this is how we can perform simple operations using arrays. A very important aspect of arrays is to pick out various elements of an array. So let us see, we have the array f. So let me print f. Suppose I want to pick out element number 2 to 4 of f. So I will simply do f to 5. So this is called as array splicing. So when I input 2, 5, it goes from, oh, so okay. So this is element number 0, element number 1, element number 2. So this has chosen element number 2. So 18 is what I have chosen from this. So this is 0, 1, 2, 3, 4. So the thing about array splicing is whatever index you put over here, it will return the n minus 1th index. Okay. So if you put 5, it will return till element number 4. So this is 0, 1, 2, 3, 4. So this gives us elements 2, 3, 4. So this is 2, 3 and 4. Okay, let me define a slightly longer array. Let me make h is equal to np dot random dot normal 0, 1, 10, and let me print what the value of h is. So now suppose I want to choose the third element all the way to the ninth element, so or rather to the eighth element. So I will do, so I can splice it using h. So the third element in this particular case is 2 because the numbering has an offset from 0. So this is 0, 1, 2. Okay, so and I will go all the way to, so this is 9, this is 8, this is 7. So this is the index number 9, this is index number 0, this is the 10th element, but the index number is going to be 9. So I want it till the 8th element, so I will simply put equal to 8. And let me assign this spliced array to something. Let me assign it to k. Then I can print out what k is. Excellent. So we have chosen from the second index. Okay, so this is 0, 1, 2, and we are going all the way till the 7th index. So 0, 1, 2, 3, 4, 5, 6, 7. Okay, so this is the last index. Another way of looking into it is the choice of the index number to the element number. But anyway, once you start using it, you will be comfortable in what it really means. You can have a look at the video as many times you want, but it should be comfortable to you once you start using it. So this is how you can splice an array and assign it to k. Now I can query the third element of k. So the third element of k will be 2. So I can print that particular element out as well. So the third element is this. So 0, so this is 1, 2, 3, but the index number is 0, 1, 2. Okay, let me print out the first element of k, that is index number 0. So it is this particular value. Okay, so the important thing to remember is arrays and matrices in fact have an offset from 0. This is very much similar to what happens in MATLAB as well, rather in C as well. In MATLAB in fact the offset is from 1. A similar notebook will be made available in Octave as well. Whatever we are doing in Python, it will be made available in Octave. I will put up the download link to these notebooks so you can download them and run them on your own computer. But in view of time, we're going to discuss some of the specifics, and whatever you're able to do in Python, you should be able to do equivalently in Octave as well. So with the help of the notebook files that you can download, you should be able to see how to do it. So proceeding, let me show you a simple booleans that you can do on various arrays. So let me print again k for reference. So now suppose I want to find out in the array k whether there are elements which are greater than 0. So let me just write m is equal to k greater than 0. let me print M as well. So M is an array which contains various booleans or logicals. So it says false, so k is not equal to 0, this particular element, so it says false. True, true, false, false, false. In fact, I can do this also. So n is equal to k of k greater than 0. So it will, let us see what it prints. So let me print n. So n only contains those elements of k which are greater than 0. So the meaning of this statement is find out the indices of k which is greater than 0 and assign them to n. Or equivalently I can write p equal to, so yeah, I mean, this is how you can obtain various conditionals without having to do a loop. So traditionally you would have to loop over each element of k and do a conditional whether ki, if I is the iteration variable, is greater than 0, it's less than 0. But now you can do a scalar operation, you can broadcast. So this particular check you can apply on all the elements of k without having to worry about doing a loop over all the elements. Okay, so we can declare array matrices as well. So in the same way we've declared the arrays, we can declare matrices as well. So let me declare a is equal to np.nd array. So let us go to the documentation of nd array quickly. So it says shape and data type. Okay, so we have to supply the shape and the data type. It will be say 2 cross 2 and the data type will be float. Let me print a. So it has initialized this array to me. I mean, whether a was declared as something like that. So it initializes a 4 cross 4 matrix which is all zeros. In fact, we can make a random matrix as well. So let me write np dot random dot normal 0 comma 1 comma shape equal to 4 comma 4. Okay, so this is how we supplied the size of the array over here. So if you look into the contextual help for normal, you will see that you have to supply the size as well. Okay, so the size is to be given as a tuple. So this is called as a tuple. Basically it's a ordered number 4 cross 4. In fact, if I can make it 4 cross 3, it will make 4 rows and 3 columns. Okay, so this is how you can create array, create matrices. So we can apply the same operations. Let me make it 4 cross 4 and a. Let me declare another array as e equal to np dot ones. So let us look into the documentation of ones, shape, data type. So the shape will be equal to 4 cross 4 and that's it. I mean, we don't need anything else. We can print e. So it creates an array in which all the elements are 1. So now we can do a matrix multiplication. So we can do np dot multiply b and e. Okay, so let us see what f is. So quite naturally, all the element wise operations, so b will be equal to f. Okay, so similarly, let me in fact declare g as twice of f. Let us print what g is. Okay, so I've multiplied all the elements of the matrix f by 2. So now we can multiply two matrices in the sense of a true matrix multiplication. So a true matrix multiplication is not an element wise multiplication. So if I were to multiply this matrix, so this entire matrix and this entire matrix, the first element of that matrix would be this row multiplied by this column. The second element would be this row multiplied by this column. So that's a true matrix multiplication, and the way to do it, so h will be np dot dot f and g. In fact, let me print out what h is. In fact, one should always use these kind of functions to avoid any ambiguity. You may imagine writing f times g. You can simply write n equal to f into g. But what is this multiplication? Is it an element wise multiplication between two numbers, or is it an actual matrix multiplication in the sense that we know from class 11-12? A matrix multiplication is not an element wise multiplication. It involves rows multiplying various columns. Okay, so it's not the same. It is not the same. Okay, so let us do the Boolean. So let us do the Boolean of, so let us choose this array G, this matrix G. Okay, so first of all we can choose various indices. So we can choose the first element. Let me print this out. Print G, and it is this first element. In fact, I can print out the first row, second column. It comes out to be this. So this is how you can pick out the different elements of a matrix. Alternately, you can do the Boolean as well. So let me print G less than 0. So it says false, true. So this is less than 0, hence this is true, and so on. So you can do all those things as well. Let me show you something useful as well. So let us declare P as np.where. So where is a kind of logical broadcasting. So let us say where G greater than 1, suppose. Okay, so let me print out P as well. So when I do P is equal to np.where G greater than 1, this particular function call will give me all the indices of the matrix G where this particular conditional is being satisfied. So where is G greater than 1 being satisfied? At row number 0, column number 3. So row number 0 is this, and column number 3 is this. Remember, this is column 0, column 1, column 2, column 3. Similarly, it's being satisfied at row equal to 1, column equal to 1. This is row equal to 1, and this particular thing is column equal to 1. Okay. Similarly, row equal to 1, column equal to 2. Row 1, column 2. So as you can see, np.where is a very versatile function where it will broadcast that conditional all over the array G or over the matrix G. It also works for arrays as well. And it will tell you all the indices where that particular conditional is true. So in this particular case, it is true for all those pairs of INJs, if you may. So then how can I get all the values where this conditional is satisfied? So I have obtained all the indices. So I can simply say, let me print out G P0, P1. So when I do G of P0, P1, this essentially means G of all those row values, column values. So G P0, P1 means G0, 3. So let me print G0, 3. So it comes out to be this first value. Then what is it? G1, 1. So we get the second value. So instead of manually writing down each value, we can simply supply whatever indices we found out. So these are the row indices and these are the column indices which satisfy that particular conditional. We will supply those row and column indices into the G to get back the values where this particular conditional has been satisfied. An alternate way of doing it, let me delete this, is simply G of G greater than 1. It gives us the same value. So there are multiple ways of getting things done in Python. I've shown you how to declare scalars, how to declare arrays, how to declare matrices, how to do some simple operations on them. As the course progresses, we'll look into the various functions that we'll find useful, and we can have a small discussion about that particular function at that point of time. I don't want to overwhelm you with so many functions. Many of you might be knowing Python, many of you might be new to Python, or in fact programming. This is a very good way of starting off programming. Have a look at this, try to implement these on your own. You may run into some issues. You can email me. You can Google is a very good resource for learning Python as well. So with this, we end this particular lecture. In the next class, we'll look at some basic programming constructs and a very simple program which makes use of those constructs. It's bye from me. Until then, have a good day. Bye.